Hello, and welcome to our lecture about waves. First, I'm going to go over the mathematics that they touch on but don't go deeply into for in the textbook, and then I'm just going to go over the examples or the types of waves that are talked about in the textbook in order to get a good theoretical understanding of what waves are, because waves are a very important thing to do when when you're studying physics. It turns when you're just talking about sine or cosine waves or Bessel functions, which are cylindrical waves, or spherical Bessel functions, which are spherical waves, then you can just then you can say that any type of function is a combination of these types of waves. I might have gone over this last week now that I think about it, but any type of function is a combination of these types of waves with different amplitudes for different wavelengths. So you can add those together. I think the actual rule is that it has to be any continuous function, but you can add these waves together and analyze problems by looking at the first few wavelengths with the highest amplitude, uh, instead of trying to solve every type of equation and every type of dynamics problem by yourself. And then another thing that's very useful about this is that it turns out, as per quantum mechanics and Einstein's uh, Einstein's earlier work, is that waves uh, or equate that light behaves both as a wave and a particle. And then quantum mechanics states that uh, matter also behaves both as a wave and a particle. So either way that you look at it, you're going to uh, whenever you get into like modern enough physics, it's like 90% waves. It's just really, really important to know as we go through this. So because of that, I want to go over what it means in order to be a wave. So first of all, uh, I'm going to say that a reminder about something that you probably learned in algebra class, is that if you shift a function by some delta x, then uh, f of x goes to f of x minus delta x. So for example, we have a Gaussian here which has the form e to the negative x squared over 2 sigma squared, where sigma is the standard deviation. It's just a constant. But if we shift the entire information, all of the function, some distance away, delta x, so we shift from here to here, with this being delta x, then it becomes instead e to the negative x minus delta x squared over 2 sigma squared. So it's the same function. It's just that you replace x anywhere in the function with x minus delta x, and that's going to give you the function. So what a wave is some sort of information, some sort of pattern that moves around uh, as if uh, with some speed v. So this is y, this is x, this is y, this is x. So if you have some pattern like this, then as it transfers, as it moves from side to side, it goes along with the same pattern, but with a distance between them of x, delta x equals vt, where v is the velocity of the wave and t is the time that has passed. So what this states for the most general form is that y of x of t, where y is whatever information, whatever you're looking at. So electromagnetic wave or the electromagnetic intensity, or uh, like a wave in a beach where the water has a certain height at a certain time, or a certain height at a certain position, and then moves around with that height, or sound wave where the pressure is different at different positions, and that's how you make out sound, is going to be equal to f of x minus vt plus g of x plus vt, where the plus vt just means that you have another wave that's going in the opposite direction with the same speed. So if you take the derivative of this, I'm going to take the time derivative first. It becomes f prime of x minus vt times negative v, because that is the derivative of what's inside of the uh yeah, the derivative of what's inside uh for the chain rule, if you remember the chain rule, plus g prime of x plus vt times positive v is equal, and then the double derivative of in respect of time is d squared y dt squared equals f prime prime of x minus vt times negative v squared, because again you're taking the derivative of what's inside, g prime prime of x plus vt times v squared, which is going to be equal to v squared times d squared y dx squared. So this gives us the wave equation where the partial derivative of whatever you're looking at, whatever amplitude or pressure or light or anything that you're looking at, is equal to 1 over v squared uh, d squared y dt squared, where these are partial derivatives. So this is the most general form of the wave equation that you're going to find. And I think it's really useful to know. I don't think I learned this until upper divisions when I was taking quantum mechanics courses. So this is just a good way to get your foot in on the ground floor of understanding physics more. And if you don't know what a partial derivative, if you have a derivative of more than one, uh, if you have a function that's dependent on more than one variable, so say y of x t equals y x squared times t cubed, then taking the partial derivative of this will only take the derivative of one of the variables without changing the others. So it becomes 2x. So the partial derivative of y with respect to x becomes 2x times t cubed, where we didn't do anything to the t because we knew that it was going to be cubed, or we knew that we are only caring about x. So that is the general wave equation. That is very important to know if you get into higher level physics, but it isn't super practical right now. So instead of doing that, what we're going to worry about is sine waves, which are sine and cosine waves, which follow this wave equation. It's pretty easy to establish that they follow this wave equation, and I think they do in the textbook. I think it's just that I found it more interesting to go over the general version of the wave equation rather than the specific sine wave equation. So what uh, this is going to give us is that y of x of t is equal to a cosine k x minus bt plus phi, where you can also have a cosine x plus bt plus another phase constant, but I'm not going to deal with that right now, where k is some constant necessary to make it so that this k times x minus bt is just a number, so it can be read by the cosine, or it can have an output when you put it in a cosine, because whenever you have a function like this, if you put in an argument, it has to be like just a number. It can't be it can't be a united quantity because of the reasons that we went over in the very first lecture. So y of x of t equals a cosine kx minus bt, and then we are going to use a little bit of logic to say that this is going to be equal to 2 pi x over lambda, where lambda is the wavelength, minus v 2 pi over period times time plus phi, because if we look at a slice, if we look at a position where either x is constant or t is constant, I'm going to say where t is constant for first, then we have a condition where every time x is equal to some variable times lambda, some variable times the wavelength, then 2 pi x over lambda goes to n times 2 pi, which is the condition that it's the condition that a wave has in order to exist, or not a wave has, a sine or cosine wave has in order to exist, is that every 2 pi, the the wave starts repeating, the amplitude starts repeating. So when you were going through your lab last week, you saw sine wave versus time, and you saw that every period, uh, which is similar to a wavelength, but for time, there was a peak that was a constant distance away from each other. So x equals n times lambda, or t equals n times t, goes to 2 pi t in lambda, or nt over t, which goes to n times 2 pi. So both of these conditions have to be true because it's a sine wave, which means that it has to repeat every period and it has to repeat every uh, wavelength. So y of x of t goes to a cosine 2 pi x over lambda minus 2 pi t over period plus whatever phase constant we want to have here. So 2 pi over lambda is equal to k, and 2 pi over period is equal to v times k. So therefore, v is equal to 2 pi over period times k is equal to 2 pi over period times lambda over 2 pi, which is equal to lambda over period is equal to lambda times f. So the speed of a wave is going to be given by its wavelength times its frequency. Okay, and then that's the main thing that I want to get to when we're just talking about waves without talking about anything in specifically. There is also one thing that I want to get to before we get to our break, which is the difference between longitudinal and uh, longitudinal and transverse waves, where transverse waves, if you look at y versus x, or y versus t, honestly, have the form of where it goes up and down and up and down, where the actual height changes as you look at the wave. So y is height in this case, instead that's what we're measuring. And then y versus x here, where y is again height. For a longitudinal wave, doesn't look like that. A longitudinal wave has some pressure that gets bigger and smaller and bigger and smaller and bigger and smaller as time goes by, but the actual height doesn't change, just the pressure. So this is kind of cheating. This is showing what pressure is when really the y shouldn't change at all. So this is more of a demonstration than a graph. So I'm just going to actually erase y of height from here because it's not really a graph, it's just what it looks like, what the pressure looks like as you go from across x. And then if you write out, instead of height being your y variable, you write out y being pressure, then this is again going to just look like a standard wave. Okay, so that's what I have to say for now. I'm going to come back 2 or 3 times to go over more specific problems, or not specific problems, because we kind of got past the point where the problem's more important than the concept, and I think that the concept is more important than doing example problems right now. So, yeah, just a second, and I'll see you then.